Okay, so our new unit that we're getting into, it's unit 4, and it's called transformations. It's going to be a little confusing. Our lesson today is called translations, so they sound a lot the same. I want to make sure we distinguish them. So the overall unit is called transformations. It's dealing with how we maneuver things on a coordinate plane, okay? And so 4.1 is translations. So as we slide down, what you will learn is how to perform translations, perform compositions. Yes, we're doing English here. We're going to do a composition today. Okay? And solve real-life problems involving compositions. This is not going to, this math, there's not tough math involved here at all. At all, at all, at all. If you know how to graph, you'll be fine, but you just need to learn some terminology. That's the main thing is, so take notes on some terminology. And here's your very first one. It's called a vector. Okay? A vector. Vector is a quantity that has both direction and magnitude or size and is represented in the coordinate plane by an arrow drawn from one point to the other. What you need to know about vectors, and I'll show you, we'll show it up close better. The diagram shows a vector. You're going to see here in a second the initial point or starting point of the vector is P, and the terminal point or the ending point is Q. The vector is named vector PQ, which reads, as I just said, vector PQ. So look over here. This is a vector. Okay? Only the green arrow. Ignore the black arrows for now. It's only the green arrow. That's a vector. It's vector PQ, and the way the arrow points tells you where the starting point is and the ending point is, right? So here the starting point is P and the ending point is Q, and the way you draw this, label it, looks almost like a ray. It just got half the arrow. So that is how you designate vector PQ. Okay? Now, if you listen to what I said at the beginning, vectors have magnitude and size. And so the way you determine their magnitude is by how they move on a coordinate plane. So this particular vector, when we start at point P, and we go to point Q, you can see that first you go 5 units to the right to get there, and then you go 3 units up. When you move to the right on a coordinate plane, is that a positive or a negative movement when you're moving to the right?
Positive.
It's a positive movement, so that looks like a positive 5, and when you move up, is that a positive or a negative?
Positive.
Positive, right? If you move down, it's negative. You move up, it's positive. So the way you designate this in what's called its component form is it looks like that, okay? With those weird little brackets. I'm sure there's a name for them. I'm sure I don't know what it is. Okay, 5, 3. And my screen just went black. There we go. Okay, so that is called the component form. When you see something that tells you to write a vector in component form, it's those 2 brackets with its numbers of translation. Erase that. All right, any questions? You got down what you want to get down? I can go forward. All right, so identifying vector components. Let's look at this one here. How would you name this vector? Holly, how would you name it?
JK.
Say again?
JK.
JK, and again, please remember you're writing with the half arrow, okay? JK. Brandon, what is its horizontal component? When we go from J to K, how far horizontally am I going, and is it positive or negative?
3 and it's positive.
So we're going 3, let's see, I go 1, 2, 3. Indeed it is. Deanna, what is my vertical component? 4. Positive or negative, Deanna?
Positive.
Positive. 1, 2, 3, 4. So in component form, that's what it looks like. Okay? Some challenging math principles right there. Any questions? We good? All right. I don't know why they threw this in the middle of the chapter. I would have thought this is how you would start out the chapter, but it's describing now again. I said this whole unit is called transformations. A transformation is a function that moves or changes a figure in some way to produce a new figure called an image. So this is the next terminology for you to write down. Okay, the new figure that you draw when you transform is called an image. Your starting or original figure is called your pre-image.
Sebastian,
Which one?
Para.
Okay, so you've got your image and your pre-image. Is he going to be gone for a
Yeah.
while?
His mom's here to pick him up.
Okay, so just watch this
All right.
recorded, okay? All right. This particular, so let me go back to here, this transformations. We're going to cover 4 different transformations, not in this chapter today, but overall in this unit. We're starting today with translations, then we're going to go to reflections, rotations, and then dilations, okay? Those are the 4 different transformations we're going to be discussing. Today, we're doing translations. So a translation moves every point of a figure the same distance in the same direction. And I'm not going to read the rest of it because it's just going to get confusing. I'd rather just show you. So our original image in this drawing is segment PQ, the blue one. Okay? They did a translation and drew what's called PQ prime, segment PQ prime. If you see these little inflections, you state that as prime. That means it's the image. This is your pre-image, this is your image. Okay? As indicated by the prime signal. Ignore these things. All this is showing is, in a translation, if you connect the corresponding points, all those lines should be parallel, because a translation does not change the size of the object or any angles. Right now we're only seeing segments. Here in a minute you're going to see a triangle, you'll see quadrilaterals, it could be anything. Okay? But that size and those angles and the orientation of that shape doesn't change at all with the translation. All that changes is where it is on the coordinate plane. That's all the translation is taking an image and moving it somewhere else in the exact same way that it was to start with, just in a different location. That's what defines a translation. Right? Rotations mean you rotate it to some degree. Reflections mean you reflect it across a certain line. And then dilations, as you think about your eyes being dilated, means it can grow or shrink. Okay? Translations just move it. So translating a figure using a vector. So here we go. We've got the vertices of triangle ABC are as follows. 0, 3, 2, 4, 1, 0. Translate triangle ABC using the vector 5, -1. So you're going to start with this triangle on these coordinates, and then you're going to translate it using this component rule. Let me show you what I think is one of the, there's 2 different ways you can go about this when you go to graphic. You decide which way you like the best. So in triangle ABC, we have our point A, which is 0, 3. We have point B, which is 2, 4. And point C is 1, 0. Our vector rule is 5, -1. Right? That's our translation. So, if you want to know the coordinates ahead of time to make it easier to graph, you just do the simple math. +5, -1. So my A prime is 5, 2. My B prime, +5, 1, is 7, 3. And my C prime, +5, 1, is 6, -1. Right? And then you go to your graph. That's fine. And you graph it. And here's what it looks like when it's done. Okay? So again, the blue image, that's your pre-image. Your original graphing points of 0, 3, 2, 4, and 1, 0. And then with your vector component of 5, -1, the red, the ABC prime, is what that now looks like. If you've done it correctly when you draw it, the 2 triangles should look exactly the same, just in a different location. Now the other way you can do this, so that's one way to do it ahead of time, or you graph the blue triangle, your vector's 5, 1, so if I'm starting here with A, and so the vector's 5, -1, then I'm going to go to the right 5, 1, 2, 3, 4, 5, and -1, I'm going to drop down 1 and put a point right there, and that's A prime. Right? So you can do it on the graph, or you can do it ahead of time and then just graph the points. whatever you find to be the easiest to do. We good? Does it make sense? JDL, you good? All right. Now here's a new thing for you to understand, a new term of how to do it. So you can write it, you can also express a translation along a vector using what's called a rule. So if you're told to write a rule of a translation, it looks like this notation right there. Okay, you write X, Y, arrow, and then you write your actual rule. So for instance, for this one we just did, our vector our component form is right there. That's called your component form. For the rule form, you write X, Y, draw your arrow, and it's X plus 5, Y minus 1. Okay? So whichever form you see it written in, component form or rule form, it tells you how to translate your image. Okay? So just know which form to write it in when you see it in your homework, your quiz, or your test. If it says write in component form, it's the brackets. If it's the rule form, it's what you see right there. So let's try this. Write a rule for me, please. It'd be nice if I had you have whiteboards, but that's fine. Write a rule for this. Here's the first thing. What is my pre-image in this picture?
The blue.
Yes, please note, okay? You might start here. This is not your pre-image. How do I know? It has the prime dashes. This is your pre-image. You're starting here, you're translating here. So please write the rule for this translation, okay? But if you write it completely correctly, Cole, you need to write it in exactly that form. Okay? Yeah, so your rule should look like this. You should have, it always starts with X, Y, and an arrow. What is my X translation?
-4.
-4. I went 4 to the left, right? 1, 2, 3, 4. What's my Y translation?
+1.
+1. Right, I went up 1 to get to A prime. And there's your rule. Should be pretty straightforward. Any questions on this? We good? All right. Translating a figure in the coordinate plane. I'm not going to even really worry about drawing this. Right? In this one, we're graphing a quadrilateral now, ABCD, with these following coordinates. Okay? And then they want you to translate with that rule right there. So if I were just to quickly just right here draw what my translated points would look like with this being +3 -1, so then my A prime, what would my A prime be? What's my coordinates for my A prime?
2, 1.
2 what? 2, 1. Right? +3 -1. My B prime is 2, 4. My C prime is 7, 5. And my D prime is 7, 1. I got that by adding 3 to every X value and subtracting 1 from every Y value. That's all. And that way, I kind of like to do it this way sometimes because then it makes it easy for me to graph. Then I just graph it by the coordinates. But if you'd rather just write it on the graph yourself and then do the translation, that's perfectly fine. So here's what that looks like. Here's the quadrilateral graph. Questions? All right, so here's the stuff for you guys to work on. Do the first two first. Name the vector and write its component form, and then you have this triangle, the vertices are as such, translate with that vector. So go ahead and do those two things first, please. graph the triangle. More easy, got it. Okay, 5, 2. That's not that, I'm sorry. 5, 3. And 9, 1. All right, so what's the name of this vector? Please note, it is not vector KB. Notice the way the arrow is going. Your starting point is B, so you should have written vector BK. Vector Burger King. Okay? What is its component form? What is our rule for how that vector translated? What does it look like? What's my x value? 1, 2, 3, 4, 5. Is that positive or negative?
Negative.
Negative 5. What's my y component?
Positive 2.
Positive 2. I went up 2. Okay? Great. So for number 2, I'm going to quickly just write the points down for my translation. My vector for number 2 is negative 2, 6. So L prime becomes 0 and 8. M prime becomes 3 and 9. And N prime becomes 7, 7. Right, so I've graphed the original here. I'm counting by 2s, by the way, on my graph just to make the image larger. So 0, 8 for L prime is here. Okay. What is it? 3, 9. 1, 2, 3. So all the way up here. 1, 2. Okay, so that's M prime at 3, 9. And then 7, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. There's N prime at 7, 7. When I connect them, you'll know you've done it right pretty confidently if the two triangles look exactly the same. Okay, if your triangles look different, you did something wrong. Okay, and you know what I mean by different. Obviously they're in a different location, but everything else, the length of each of the 3 sides, the angles, and the orientation of the triangle in space should not have changed if you did it right. Any questions on that? All right. Number 3 says, back in example 3, write a rule to translate ABC prime back to ABC. So let's do that really quick. Let's go back up here to example 3, which is here. Okay. And we're writing now in reverse, starting with ABC prime, going back to the pre-image of ABC, write in rule form what that would look like. What's that translation look like? Over here, erase, ready. So you're writing in rule form, of course. You do x, y first with the arrow. What is my translation for x? JD Ellie, what's my x translation? Going from red to blue.
4.
Positive or negative?
Positive.
Positive 4, right? I'm going from here over to here. I went 4 to the right, so it's plus 4. And Sebastian, what's my y translation?
Negative 1.
Negative 1, I went down 1. Right, so that's what your rule should look like. You started with A prime, I went 1, 2, 3, 4 over to the right, which is positive 4 on the x. I went down 1 to get to the A, so that's a negative 1 on the y. Okay? Questions on that? All right, and the last thing, I think we're just graphing again. I'm not worried about graphing, I'm gonna keep us moving to get done. But as you would see here, it's just written in rule form instead of component form, right? You would just add 1 to the x value and add 2 to the y value. Does that make sense what you do in there? Everybody good? Brandon, good? Great. All right, just again, they're just throwing random thoughts as they go through the book. It's just kind of odd how this works, but a rigid motion is a transformation that preserves length and angle measure. Another name for a rigid motion, how do you say that word? Anyone want to take a stab at it? Isometry, not isometry, isometry, right? Isometry. A rigid motion maps lines to lines, rays to rays, and segments to segments. Understand it, again, what were the 4 things I said we're going to end up covering? Can you name what those 4 transformations are? Translations,
Dilation.
rotation, reflection, and
dilation.
dilation. 3 of those 4 are rigid motions. Which one is not?
Dilation.
What's that? Dilation, because dilation changes the length. Okay? The other 3 are rigid. They preserve the length and the angle relationships. All right, moving on to our next thought. Compositions. Composition of transformations. It's very simple to understand what a composition is. It's when you do more than one thing. Okay? Today in this chapter, we're going to do more than one translation, but as we build with the others, you may do a translation followed by a reflection. That's a composition. So a composition is 1 or more rigid motions together. Okay? So performing a composition. Graph, what is this called here? By the way, how do we say that?
Segment.
Segment RS, yes, going all the way back to our very first chapter ever, right? Graph segment RS with those endpoints of -8,5 and -6,8, and then its image after this following composition. So you see here we have 2 translations, okay? So you do one translation, and then from there, you do the other translation, okay? And here's what it would look like. So the blue, of course, is our pre-image, our starting point. Our first translation was you added 5 and you subtract 2 from the y, okay? And then your second, so then you get RS prime, the red line, that's your image. But then your next translation is you subtract 4 and you subtract 2, and you get RS double prime. Okay, so you went moving to follow the arrows, you went from blue to red first, and then from red to green. Okay, the main thing to remember is you don't go back and do the second translation from here, you do it from here. Now, something else to note is this. Let's do a little bit of math. Very challenging math. Let's add those together. What does that net mean? X what?
Plus 1.
X plus 1. And Y minus 4. So if I go back to my 2 starting points, -8,5 and -6,8, and I apply this net result, then my final translation coordinates should be -7, 1, and -5, 4. You following where I got that from? Right? Just took this to here and here. And so then if I look at my final image, the green one, those should be my coordinates, -7, 1, and -5, 4. And look at, there it is. Okay? So you can do a net composition to get where you want to end up at.